Time to study for my physics test. Me, 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 me. Me, 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 me. Oh shoot, it's late. I don't have time to read this whole book. Guess I'll have to look up to YouTube for my studying. First things first, projectile motion. Oh, here's a video.
I hate baseball. It's so boring.
Maybe it's boring because you don't know the physics involved in it.
Garcia sends it and sends Carroll back. He's at the wall, and the legend grows. Deals to Altuve, who launches the first pitch.
Although seeming simple at first, America's favorite pastime has a plethora of physics behind it.
Singles scored in the first. Swinging a drive out to right field. That one's got a chance. And it's
Let's take this home run by Ha-Seong Kim of the San Diego Padres for example.
in the air to left field. Back goes De La Cruz at the wall. Grand slam! It's Slam Diego for Ha-Seong Kim. His first
The first thing we can analyze is the initial pitch. Let's calculate the speed. The ball moves 60.5 feet in about 0.425 seconds, meaning it was going about 142 feet per second, which we can multiply by 60, the amount of seconds per minute, to get about 8,541 feet per minute, which we can multiply by 60 again, the amount of minutes per hour, to get about 512,470 feet per hour. And then to get miles per hour, we can divide that by 5,280, the amount of feet per mile, to get about 97 miles per hour. We can make where the ball lands the positive direction for the x-axis, letting perpendicular be the y direction. So we need to use trigonometry to calculate the velocity in each direction. First, we need to find the angle between the pitcher's mound and the landing spot by using a protractor and a model of the hit. And we can find that the resulting angle is 62 degrees. Next, let's solve for the adjacent side of the pitch velocity. For this, we need to use the equation cosine theta equals adjacent over hypotenuse. So now we can insert the values. The new equation would be cosine 62 equals adjacent over 95 miles per hour, with the hypotenuse being the exit velocity. We can then multiply both sides of the equation by 95 to get 95 cosine 62 equals adjacent, which simplifies to about 45 miles per hour in the negative direction.
Now I can fall super far.
Next, we can analyze the hit. In order to figure out the force Kim exerted onto the ball, we need to figure out the acceleration of the ball. And in order to figure out the acceleration of the ball during the hit, we need to know its impact time and exit velocity. And thanks to radar guns, we know that the exit velocity is 95 miles per hour in the x direction. But because of the sheer speed of the impact, it is impossible with the information we are given to calculate time. So the acceleration was essentially the difference in velocities divided by the time, or 140 miles per hour divided by time. Now let's draw a free body diagram of the situation. As you can see, there are two forces acting on the ball, the force of gravity and the push force of the bat. Next, we can use the equation of Newton's second law, or net force equals mass times acceleration, to figure out the push force. First of all, the average mass of an MLB ball is 0.34375 pounds, so we can use that for mass and to calculate a part of the net force by multiplying it by 32.1740 feet per second, or the gravitational acceleration, to get 11.0598125 pounds of force. We can also use trigonometry and the Pythagorean theorem to find the sum of the force of gravity and push force. First, we need to find the x and y components of the push force using trigonometry, with the launch angle 29 degrees being our angle. For the x component, we can use the equation cosine theta equals adjacent over hypotenuse, and to solve it, it will look like cosine 29 equals adjacent over push force, or 0.8746 push force. For the y component, we can use the equation sine theta equals opposite over hypotenuse. And to solve, it will look like sine 29 equals opposite over push force, or 0.4848 push force. So the equation we can use is the square root of 0.8746 push force squared plus 0.4848 push force minus 11.0598125 squared equals 0.34375 times 140 divided by time. From this we can solve that the push force is equal to 0.3475 times 140 divided by time divided by 1.3594 plus 8.1358044.
That's a lot of numbers.
Now it's time for the main event, calculating the hit distance and air time. First we need to separate the x and y components of the velocity using trigonometry. The launch angle of the hit is 29 degrees, so theta equals 29. To calculate the x component of the velocity, we will use cosine theta equals adjacent over hypotenuse, and to calculate the y component, we will use sine theta equals opposite over hypotenuse. So the equation for the x component is 95 cosine 29 equals adjacent, which equals about 83 miles per hour. The equation for the y component is 95 sine 29 equals opposite, which equals about 46 miles per hour. Because we are going drag in this unit, there are no forces acting on the x-axis. So the x component of velocity remains the same throughout the whole flight until it eventually lands up in the stands. So now we will use the y component to calculate flight time. Let's use the kinematics equation. V equals v naught plus a times t. This will calculate the time it takes for the velocity to reach zero, or the maximum height, with the gravitational acceleration negative 32.174,000,2667 feet per second squared, being the acceleration. If we input the correct values, we should get 0 equals 46.056911392 minus 21.936818 which solves for half air time, which equals 2.099525715 seconds. So the air time would equal 4.19905.143. But that was if it was landing at the same height that it landed before. But that is not the case. So we actually have to graph this as a parabola, and in order to do that, we have to find the vertex, or x distance, comma, maximum height. We can use the equation d equals d naught plus v naught t plus half acceleration t squared. The initial height would be the height that the ball was hit from, or about 2.875 feet. So the equation would be d equals 2.875 plus 67.550140416, the y component of velocity in feet per second, times 2.099525715 plus half of negative 32.174,000,02667 times 2.099525715 squared, or d equals 73.78662843 feet. Now let's calculate the distance when dy equals 73.78662843, or time equals 2.099525715. We can use the same equation we used for dy. Dx equals dx initial plus v naught t plus half of a times t squared. When we insert the values, we get dx equals 0 plus 121.86367919,733 times 2.099525715 times 1/2 times 0 times 2.099525715 squared, or dx equals 255.8559282 feet. Now we can put this into vertex form to get 7 equals a times x minus 255 0.8559282 squared plus 73.78662843. So now we need to solve for a. We can put the y-intercept of 2.875 into the equation to solve. This will get us 2.875 equals a times 0 minus 255.8559282 squared plus 73.78662843, which we can solve to get a equals negative 0.00108324449489838. So the equation for the parabola is y equals negative 0.00108324449489838 times x minus 255.8559282 squared plus 73.78662843. We then need to figure out the slope of the stands that the ball lands in. The slope of the stands is 0.5 feet by 3 feet. The intercept between the stands and the parabola is 467.257 feet and 25.376 feet. So essentially this is saying that the ball landed 467.257 feet from home plate and 25.376 feet off the ground. This is only an estimation because we cannot account for drag, which would drastically decrease the distance from home plate and slightly decrease the distance from the ground. So in order to make a correct estimation, we need drag, but that's for another lesson. So today we used trigonometry, made a free body diagram to show the forces exerted onto the baseball, calculated the force of gravity on the baseball, calculated the push force the bat exerted onto the ball, split the velocities of the ball into x and y components, calculated the flight time of the ball, and calculated the distance the ball traveled.
I changed my mind. Baseball is fun. I hate massive dingles with physics.
Home run!
I don't know if I understand that. How about this video?
Wow, I wish I could be as big and strong as that guy.
Good news, kid. One day you can. But do you have what it takes?
To see what it takes, let's look at this clip of the first half-ton lift documented. First, to analyze this video, let's find all the forces acting upon the barbell while at rest. Drawing a free body diagram, in this instance, the only forces acting upon the barbell are gravity and normal force. So let's find the force of the barbell acting on the floor. By looking at the video, we can see that Eddie Hall has 9 25 kilogram plates and 1 15 kilogram plate on the barbell on each side, making a total of 18 25 kilogram plates and 2 15 kilogram plates on both sides. Adding the mass of the Olympic barbell, we get a total mass of 500 kilograms. We then multiply 500 by the gravitational field strength of Earth, 9.81 newtons, to get the gravitational force of the barbell acting on the floor, which is 4,905 newtons in the downwards direction. Because of Newton's third law, which states for every action there is an equal and opposite reaction, we know that the normal force is also equal to the force of the barbell acting on the floor, meaning the normal force is 4,905 newtons in the upwards direction.
Wow, I can't even count that high.
Next, we analyze the deadlift itself. Let's start with the upwards half of the motion. First, let's make sense of the variables that are given to us. We can determine that the final and initial velocity are 0. Since we can observe that the movement is constant, we can also put the acceleration as 0. Next, we can use math and a little magic to estimate the rest of the variables needed to find the upwards velocity of the barbell. Measuring the clip, we can estimate that the time of motion is 4 seconds. Next, we can find the initial displacement and final displacement using these two pictures of Eddie Hall. To find the height of the bar when it is at its maximum height, we can take the second picture of Eddie standing fully straight and use the ruler to measure how far the bar is from the ground. Then, we can measure how far the top of Eddie's head is from the ground. Since we know Eddie Hall is 1.905 meters tall, we can then set up a proportion and find the height of the bar from the ground, resulting in the maximum height the bar gets from the ground being 0.78 meters. We can repeat this process for the first picture to find the height of the bar when the barbell was at rest. This ends up being 0.24 meters from the ground.
Huh?
Finally, using this information, we can now find the average velocity of the barbell during the upwards motion. Using the equation d equals d naught plus v average times t, we can plug in all of our variables, and it looks like 0.783 etc. equals 0.245 etc. plus v average times 4. This simplifies to v average equals 0.13 meters a second. Now for the downwards movement. To analyze this, we'll find the instantaneous velocity of the barbell the moment before it hits the ground, and the air time of the barbell as it drops. Since this time is a lot shorter, it is much harder to get an accurate estimation like we did before. Instead, this time, no pun intended, we will use the equation d equals d naught plus v naught times time plus 1/2 times acceleration times time squared. Let's think through our variables again. We can set 0 as our initial velocity and displacement, and negative 9.81 as our acceleration. For our final displacement, we can subtract the maximum height of the bar from the initial height of the bar when it's resting on the ground. This results in negative 0.54 meters. Now, with all of our variables, we can solve for time. Plugging them in, we get the equation negative 0.54 equals 0 plus 0 times time plus 0.5 times negative 9.81 times time squared. This simplifies to 0.33109 etc. seconds, or 0.331 seconds. Next, we calculate the velocity. Using the equation v squared equals v initial squared plus 2 acceleration times parentheses d minus d initial, we can plug in our variables and get v initial equals 0 plus 2 times negative 9.81 times negative 0.5377061. This simplifies to 3.25 meters a second downwards.
Wow, is there anything else you can show me?
Why, yes I can.
Here's a clip of the world's first 100-pound one-armed curl.
Wow, so impressive. What's the physics behind that?
Funny you ask. This is an example of basic circular motion.
Tell me more.
Well, kid, we can find the arc length and the magnitude of the average angular velocity of the weight moving using simple algebra. To find the arc length or the distance traveled of an object in circular motion, we can use the equation theta equals arc length times 360 over 2 pi r. We can rearrange this equation to equal arc length equals theta times 2 pi r over 360. Now that we have our equation, all we need to do is find theta and r. From an inside source, we know that r is 0.3 meters, so all we really need is theta. To find theta, we can take a protractor and measure the distance the arm moves. We can observe that this is 130 degrees. Since it moves both up and down, we'll have to multiply this by 2. Now that we have all of our units, we can plug them into the equation and get our answer. When we plug all of our units in, we get the equation S equals 2 times 130 times 2 pi times 0.3 over 360. This simplifies to 1.36 meters. Lastly, we'll find the magnitude of the average angular velocity of the object throughout the motion. To do this, we'll use the equation velocity equals delta over time. Since we already know delta, all we need to do is measure the time. The time is about 6 seconds, and plugging our numbers into the equation, we get 43.3 degrees a second.
That's a lot. Thank God it's over.
Hold on there, Buster. While our answer might be technically right, the standard unit used by physicists are radians, not degrees.
Oh, so how do you change degrees into radians?
We can do this by multiplying our answer by 2 pi over 360. This turns our 43.3 degrees a second to 0.76 radians a second.
Wow, teaching me all the physics behind lifting inspires me to hit the gym. One day I want to look like you.
Remember, little bro, with enough time, effort, and most importantly, steroids, you'll be looking just like me.
Now I have to study circular motion. Ugh, there's not even any videos on circular motion. How am I ever going to study this in time? Oh, I found one. It's from 2006 and has no views. Guess I have to give it a try.
How do you find net force again?
Force is equal to mass times acceleration.
Ugh, physics is so boring. Can't we go somewhere fun like an amusement park?
Well, actually, there's tons of physics at amusement parks. For example, let's take a look at this roller coaster loop from the California Screamin'.
To start, let's find the tangential velocity. But first, we will need some variables and a definition for uniform circular motion. Uniform circular motion is when an object is traveling in a circle at a constant speed. Now let's find the variables we need. Google tells us that the radius of the loop is about 6 meters, and when watching the video, you can see that the loop takes around 2 seconds to complete. So in order to find the tangential velocity, you can use the equation v sub t is equal to 2 pi r over t, which when you plug in the values, gives you v sub t is equal to 2 pi times 6 over 2. This gives us 9.42477796 meters per second as the tangential velocity.
Wow, what else can you do?
Well, we can also find the roller coaster centripetal acceleration.
Wait, didn't you say during uniform circular motion, the object's speed is constant, so wouldn't the acceleration be 0?
Well, I can see how you would think that, but acceleration is the object's change in velocity. And since velocity is a vector, that means that when the direction of the velocity changes, the acceleration does too. And the official definition for uniform circular motion is actually the acceleration that causes a change in direction. And centripetal means center seeking.
Boring, let's get to the math.
Alright, fine.
The equation for centripetal acceleration is a sub c is equal to v squared over r. Plugging in the variables gives us a sub c is equal to 9.42477796 squared over 6. 9.424 squared is 88.82643696, and when you divide that by 6, you get a sub c is equal to 14.8044066 meters per second squared towards the center of the circle.
Ah, I see. Tangential velocity is the speed an object rotates, and centripetal acceleration is the speed an object moves towards the center.
Close, but no. You said rotate, but the object is actually revolving.
Isn't that the same thing?
Not quite. So rotation is when an object is spinning around its own center axis, and revolving is when an object is spinning around another object. For example, the Earth revolving around its own center causes the day and night cycle, while the Earth revolving around the sun causes the seasons.
Oh, I get it now.
Yup. So now we're going to be talking about centripetal force.
Another centripetal thing.
Yeah, centripetal force is also directed towards the object's center, and is either one or the sum of multiple forces. For uniform circular motion, centripetal force is also equal to the net force, and can be found using the equation centripetal force is equal to mass times centripetal acceleration.
That's a pretty easy equation.
Yeah, it does seem that way. However, we're going to need to do a little bit of research to find the mass of the roller coaster cart.
How long will that take?
I don't know, but you're going to help me find out.
Fine. Finally.
Oh, did you get it?
Yep, California Screaming has 6 4-seat carts.
On average for a metal roller coaster, a 4-seat cart weighs 1,020 kilograms, so the whole thing should weigh 6,120 kilograms.
Nice. All that's left to do now is some simple arithmetic.
The equation for centripetal force is F sub c is equal to m times a sub c. When plugging in the variables, you get that F sub c is equal to 6120 times 14.80440066. When you multiply that together, you get that F sub c is equal to 90,602.9684 newtons.
Alright, we're done here.
What about centrifugal force?
Well, centrifugal force isn't actually a real force.
Yes, it is. When I'm in the back of the car and we turn right, I get moved to the left.
Well, that's actually a result of inertia, not some new type of force.
What's inertia again?
Inertia is an object's resistance to change in movement. So in your example with the car, the reason you're pushed left is because when the car is moving forward, your body's trying to keep moving straight, and when it turns to the right, as a result, your body's forced to go left.
Wow, I guess physics wasn't too boring after all.
Well, now I have to do is take the test.